Hello everyone and welcome to today's lecture. Today we'll be talking about how to measure angles in radians and degrees, an introduction to trigonometric functions, and we'll be talking about how to use trigonometric functions to determine the geometric relationship between angles and distances. So to start off, what I want to do is first discuss the two types of units that we use to measure angle in mathematics. And the names of these units are called radians and degrees. For notation, what I'm going to do is I'll call, if an angle is measured in radians, we'll call it theta with r as a subscript. And if an angle is measured in degrees, we'll call theta with a d as our subscript for the angle measurement. So the main idea here is that these angles are always measured with respect to some sort of rotation around a circle. So if we have our x-axis and our y-axis, and we'll do a circle here. That's we'll put it centered at the origin of the x-axis and y-axis. We can talk about an angle measured from the x-axis as follows. Typically we use the notation theta to denote that angle. And the idea is that what's going to be of very, very important, central importance to us is what's called the unit circle, or the circle with radius 1, because it turns out that this is what we're going to use to actually define our trigonometric functions when we get to trigonometric functions a little bit later on in the lecture. But really, you can take a circle of any radius and talk about the angle measurement as you move around that circle. So if we measure an angle theta in radians, right, this angle theta, or theta r, is essentially telling you how far around the circle you're moving. So it's really, we can think of it as a ratio, theta r, where theta r is the angle around the circle, and you can go a total of 2 pi radians. 360 degrees is the same thing as 2 pi radians. So theta r is really a ratio over 2 pi. And the relationship between radians and degrees is that if you measure a certain angle in radians, theta r over 2 pi, that's going to be the same thing as the angle measured in degrees over 360. So to convert from radians to degrees, this is the relationship that we have to use. We use the fact that the ratio of the angle measurements are equal regardless of whatever units you choose to use to express that angle. So for instance, if you have an angle in degrees and you want the angle measurement in radians, right, the angle measurement in radians, theta r, is just going to be 2 pi over 360 times the angle measurement in degrees. or vice versa, if you have the angle measurement in radians and you want the angle measurement in degrees, the angle measurement in degrees is going to be equal to 360 over 2 pi times the angle measurement in radians. And that's just taking this fundamental equation, or the fundamental relation that the ratios of the angles, regardless of the units you choose to measure the angles in, are going to be the same. They have to be the same. So this is the correct way to convert angles from radians to degrees. So there's a number of different examples of how to do this in the book. If you want more examples, I can go over some examples when we talk in our office hour session. But the main idea is that using this idea in a little bit of calculus, I'm not going to get into it, how to actually show the next result. We can talk about something called arc length. So this is going to be the next concept that we're going to talk about. And arc length is a topic that is actually defined for any curve. You can use some calculus 2 to define arc length for any curve at all. But it turns out that what we're going to be interested in this class is just arc length for circular curves, or circular segments. And it turns out that if we take we'll take a circle, and this circle that I'm talking about here does not have to be a unit circle necessarily. It can be a circle of any radius. But if we take our circle, let me just get it to draw. We take a circle, say, of some radius r. And we're assuming that we're also at some angle theta. This angle, I'm just going to call it theta because it can be measured in either degrees or in radians. But it turns out that to determine the arc length along this circle, or say the length of a segment of the circle, which will be this segment right here, so the actual physical length of this red curve that I'm drawing right here, this segment, you can go through and show that this has to be equal to the following, and I'll show how to do this. We'll call the arc length S, and one of the big things that we have to that you can show is that is similar to our argument from before. It's not a rigorous proof, but it's a nice, quick kind of justification of the following formula that we're going to show. Or this is the x-axis, and this is the y-axis. The arc length of this segment divided by the circumference of the circle, which is 2 pi r, this ratio has to be equal to the angle over 2 pi. This is saying that the ratio of the length of this to the length of the entire circle, the circumference of the entire circle, this ratio has to be equal to the angle over the angle around the entire circle. Or these two values have to be similar to one another. So you can prove this using geometry, or you can prove it more generally using Calculus 2, which is something that I typically do in my Calculus 2 course. But if we take this equation and we solve for s, we end up getting that s is equal to 2 pi r times the ratio theta over 2 pi. And this 2 cancels with this 2, this pi cancels with this pi that we're dividing by. And therefore, the arc length of any segment of a circle is just the angle theta times the radius r. So this is the first big result that we have. This is saying that no matter how far along you move along the circle, you can always determine the length at which you move, which is very, very useful. It's a useful formula for a number of different applications, but specifically if you're talking about a ship traveling along the ocean, or a plane traveling around the Earth, staying at a constant height. This equation is very, very useful in terms of determining the total distance traveled along that path. And this is not just for those applications, but for really any application where you have circular motion. This is a very, very useful relationship. Another very, very useful relationship that you have is again, it's directly applied to motion. It's if you have angular motion. So if you have angular motion, you're not just going to have this arc length that you're going to have to consider, but you're also going to have to consider the rate of change of arc length along the motion as you move along the motion, as you move, say, along that circular path, along that segment. And it turns out that we have a concept here that we can directly apply, which is called the angular speed along a path. And we really do need some calculus to really understand these concepts and derive some of these concepts, but as long as we have, say, a constant angular speed, we can go very, very far without actually having to use calculus. The analogy here is from what's called kinematics, and in kinematics, you have a relationship saying that if you're moving at a constant velocity, the displacement, or the distance that you move, we'll call it not x, but I'll call it d, is equal to the velocity, a constant velocity, I'll put v naught here to denote that it's constant, multiplied by the amount of time that you're moving at that velocity. So if we have, say, constant angular motion, constant angular velocity, we can also talk about this relationship only in terms of angles. The idea directly being that you could say that if you're moving at a constant angular speed around, say, the circle right here, so along this path, you could say that theta, the angle as a function of time, is equal to what's called omega naught times t, where just like this relationship right here, omega naught is what's called the rate of change of the angle with respect to time. So the angular velocity, or the angular speed with respect to time. And this gives us a nice relationship for omega, just like with velocity itself. And you can say v naught if it's constant, but it doesn't have to be constant. So the idea is that this is a more general relationship, if you want to think of it that way. But using what we know about arc length, we can actually go through and say that, well, the arc length is equal to it's changing at a constant rate. So that you could say, use this expression right here if you're moving at a constant angular speed to show that the velocity along the curve, or the speed, the tangential speed along the curve at any given point, say right at this point right here, your tangential velocity v at that point is directly related, and it comes directly from this formula right here, that v, right, is equal to s over t, or if s is r theta over t, then your tangential velocity is equal to r times omega, because theta is equal to omega times t. So the tangential velocity, if you're moving at a constant velocity, is just omega times r. And this gives us a relationship to always, at any point, if you're moving along a circular path, it gives you a formula using the rate of change of angle. Right? Omega here is the rate of change of the angle with respect to time, or the angular velocity with respect to time. And this relationship right here gives you the relationship to solve for, say, the tangential speed at any given point, given that angular velocity. It's saying that it depends both on the angular speed and on the radius of the circle that you're traveling around. And the last main formula that we have here that is more of a geometric formula that we have to think about, and that has to do with measuring, say, the area of a segment, or the area kind of surpassed as you move along a circle on a given angle theta. So say in this picture that would correspond to this blue area right here, all of this stuff. And again, using this requires, to prove this formula, a little bit more than what we're about to do here. Requires a little bit of calculus too, but we can get away, just like we did before, by just thinking about the ratio of constant terms, or what ratios have to be equal. And the main idea here is that we always want to argue based on the circle, because the circle is the shape that we're assuming. This is the path that we're kind of moving on, say, if we have motion, or if we're talking about, say, not motion, but another example, we're going to use the similarity of the circle to derive this formula for this area A. This is the area of a segment of the circle. And we turn off the blue here. Turn it back on black. So just like before, we know that the area of this segment, we'll call it A, divided by the total area of the circle, which is pi r squared, has to be equal to the angle of the segment divided by the total angular amount if you go around the circle for one revolution, because this segment is similar to the entire circle as a whole. So what that means is, if we solve for A, or we're looking for this A, the area of that segment, then A is going to be equal to pi r squared multiplied by theta over 2 pi, which gives us the formula that A, the area of the circle, or the area of the segment of the circle, pi's cancel out, and this area is theta times r squared over 2. So we have a nice compact formula for the area of any segment of the circle, just given the angle surpassed along that segment. And this formula can be used to do many different things, but one of the big applications of this is to Kepler's laws, where Kepler's laws relate the period of rotation of the planetary objects and planets to the area that those planets span out or cover as they rotate around, say, the sun, or rotate around other celestial bodies. So Kepler's laws are a big application of this formula right here, and just this whole idea, all of these, say, these formulas that we've been talking about. So Kepler's laws are a big application. Let me make that a little bit nicer. Kepler's laws of planetary motion.